Okay, so we're going to talk about scatter plots and what those are. So a scatter plot is a graph that relates two different groups of data. So equally important, one of them's on the x, one of them's on the y, and you try and see if there's any sort of relationship between the points. Like, do they typically tend upwards? Do they clump together on certain values? And so on. Here's a nice range that you can see all the different types of correlation. First, notice that the values can go from 1 to 0 to -1, and then all of their names are present here for you. So a high correlation or strong correlation is when it truly resembles a certain function, and we're just going to be talking about lines. So if they are really strongly correlated in a line like this is, we call that a strong correlation. And the positive, negative, so all these over here are positive, and that's because they all are going upwards, okay? If it goes downwards, it's negative, and that translates on this. This is called R, which is called the correlation coefficient. It's a special number that tells us how correlated something is, how tight those dots are, and whether it's going up or down, okay? So a line of best fit is a line that we can draw between highly correlated points and lowly correlated points too. And a residual, we're going to talk about a few of those today, is how far off your observation was from what should or what was predicted to happen. Okay, so let's just learn this by just doing some examples. So is this a positive or a negative correlation? It is negative because it goes down. And is it strong or is it weak? It's probably somewhere in the middle. I would still probably call this a strong correlation, but I want to say strong weak. It's somewhere in the middle. They are you can tell that they kind of tend in a line, but they're not super clustered towards it. Okay, so with these sort of graphs, we can estimate this blue line is our goal, is to find the line of best fit. So B, remember, is the y-intercept, and which is at around 140. And they also want to compute the slope. So it seems like if we go down 5 and over 2, that would be our slope. Remember, it's rise over run. Oh, I made a mistake, didn't I? Because these blocks are 5 as well, so it actually went over 10. So the equation of this line is going to be -1/2 x plus 140. Okay. And with this blue line now, we can predict any value given the age. So if we have a 60-year-old, all you got to do is just plug in for x that age amount, and we get 110 beats per minute. Okay, and this is asking what's the residual at 40. So we look at just 40, and we want to know, hey, what was the actual point minus the predicted point? So the actual was at 130, and the predicted, if we look at where that blue line is, it's at 120. So this is 10 beats per minute, which means that our observation was 10 beats per minute off of what it should have been, according to our line. So same idea. This is a positive correlation. It goes up. It is a strong correlation. Look how close those dots are to that line. The y-intercept looks like it's around 1,000. The slope, we want to slowly scan all of these intersections, and honestly the one that's the closest to this grid here is this one right here. So that is at 5,2000. So what's the slope? Well, to get from B to that, you got to go up 1,000 and over 5. So I got around 200 for my slope. If I want to make that into a line, I just use mx plus b. Okay. Using your equation for the line of best fit, what's the predicted 12-day vacation cost, which is way beyond our graph. But if the vacation was 12 days, which is the x-axis, right? We would just take that and plug that in for x. So this is 2,400 plus 1,000, that's $3,400. Here we go. And then on a 3-day vacation, the cost was $1,500, but the prediction was 1,650. So you always still do actual minus predicted. And that's up there at the top of the page for you. So we got a negative residual, which means that the prediction was lower than, I'm sorry. It looks like the 3-day vacation cost was, or actual, was smaller than the prediction. The prediction overshot what we actually had, okay? And then we have this data here, and I want you to go plug that into Desmos, but if you don't have that open, or you just really don't want to, I do have it available for you here, and I won't force you to do this on the test. So I plugged in all of it. I was actually just finishing plugging it in. So on Desmos, you just go and create a table, which you can do from the plus sign. And then I just typed in the table exactly how it was. Okay. This little magnifying glass down here can zoom me into my data. So this looks like it's pretty strongly correlated. And if you type in this thing I typed in here and you turn it on, it gives you the line of best fit. So that's really, really cool. So some things to notice is this is positive correlation, strong. And we're just going to have to probably come back to it, but we can also see the equation down here. This looks a little off. 1 second. That should be a 2. I may have typed things in a little bit. Oh no, that looks good now. Oops. Okay. So with that, we see that it was going up, and it was pretty tightly bound to that line there, pretty close. So the graph as a whole leads us to believe that the effect on temperature, what is the effect of temperature on ice cream sales? And we can kind of see that since it's, as we go to the right, we go up. That's what positive means. So as the temperature increases, the sales increase, which makes sense. No one wants to eat ice cream if it's like 30 degrees outside, you know? But as it gets warmer, people probably would crave ice cream a bit more, right? Or maybe more people are out and about when it's warmer, okay? If we go to Desmos, you can find out what A and B are. And I'll point that out to you. They're at the bottom where it says parameters. That's A and B. Okay, so I just copied those for you. And what's the prediction of ice cream sales when X is 9 degrees Celsius, which I believe is like around 45 degrees Fahrenheit, somewhere in there. But just like before, you plug that in for X because the X axis is temperature. And we get Only $111. That's so small compared to the other days. Okay. So the prediction was this, and let's see the table entry that we had. I think it was this one. If we go up on our table and find 15.2, that will be right here. So it's saying, hey, could you compare the prediction to the actual? So we know that the residual is actual minus predicted. Okay. So actual would mean that this is, actual is like the true data point, not the prediction. So it's 332 minus the prediction. Okay, so that'd be $34. Now residual is saying that's the difference between what should have happened and what actually happened. Okay, the predicted is what should, it comes from the line of best fit. Okay. All right, so I think I'm going to no, actually, I'll do this with you. It'll just be a little bit longer of a video. A linear scatter plot would be something that forms a line. Nonlinear would be something that doesn't. So basically just a scattered mess could be nonlinear. But something like this, where it arcs like this, a little quadratic action, that's not linear either. Okay, but we're only dealing with linear. So here's an example. We are going to plot cat age, cat dog age, versus human age. Okay, so we're going to count by twos since we go all the way up to 21. And for the human years, maybe we'll count by tens. All right. So let's just plot all these points. So 0.5, 10 is right here. 1, 15. 2, 24. 4, 32. 6 goes to 40. 8 goes to 48. 10 goes to 56. 14 goes to 72. 18 goes to 91. And 21 goes to 106. So this is, now you're going to use a ruler and try and balance it so you have about the same number above and below. So mine actually looks a little off. I want to shift him down a little bit. And just try your best. But that looks like it connects the dots pretty well. So we're done here. We're done here. Coordinates of 2 points on the line. How about this one? And this one. I think this one's probably should be pretty close. I don't want to pick that end point because it's pretty far out there. So my 2 points were the second one, 115, and I'm also going to do 18 and 91. So you got to use 2 points to find an equation. Okay? So 2 points, you can find slope. I want to do this over here. So the slope is going to be y2, 91, minus 15 over 18 minus 1. So the slope should be 76 over 17. Let's make sure that's right. Yep. And let's go ahead and divide and get a decimal, because that's probably not going to go unevenly. So this is around 4.47. Okay. So remember, once you have the slope and a point, you can use point slope form. So all you do is you just plug in the y value that you want to use, the slope, and the corresponding x1. Okay? And it doesn't say, but we're going to put this in y equals mx plus b. So I'll distribute and then add 15 to both sides. -minus 4.47. So it's x. Okay. There's our equation. So this is the equation of that line of best fit that I drew. So according to your equation, what happens to the corresponding human age as the cat or dog ages by 1 year? Well, that's exactly what the slope is telling us, right? As you move 1 to the right, you move this much up. So if x increases by 1, y increases by 4.47 years. Okay? Good. Use your equation to find the approximate human age equivalent to that of a 15-year-old dog. So just like the ones we've done, the dog age is an x value, so we just toss that in there for x, and then we will just calculate that. So I got 77.6 years. Okay? So a lot of review from when we did lines, but this is taking it a little step further. Okay? So if you have any questions on this, let me know. This is some homework for you to work on. Yeah, so just, you guys got to come out and reach to me, okay?